Okay, so good evening, everyone. So we'll start from today from the cavity model of metasurface, cavity model of patch antenna. So Nandana, can you confirm, is this being recorded? Uh, you can
Yeah,
see that Teams is recorded, right?
yeah, record. Yeah.
Okay. Okay. So yeah, just to recap. So last week, what we started from is that so we discussed a small portion of cavity model of microstrip antenna, and we saw that it was very important because you can have a view of field configurations of microstrip patch antenna, and these field configurations are very important, because those are the fundamental understanding you can have for any device in electromagnetics, right? If you know the electric and magnetic field diagrams or configurations, you can have a lot of intuition and understanding of any device. And basically, so here what happens is that uh, they consider as if it is a metallic cavity. Okay, so how the cavity is formed is like in the top side. Here in the picture you see the top layer or the patch is there in metallic, and in the bottom we have the ground layer, that is also a copper layer. In between it is filled with a substrate or dielectric. Okay, so it is kind of a dielectric loaded cavity, right? So now what happens that because of now when you excite it with some kind of excitation or high frequency excitation, so there will be charge excited on both layers, both the metallic pairs. Obviously it will have charges. So here there will be two main mechanisms. One will be attractive, another is repulsive. So so obviously because of because it is a AC field, because our excitation is a high frequency and change time varying field, there will be both plus and minus charges, right? And the attractive mechanism is between opposite charges, that is on the same layer, in the same layer as well as a defined layer. That means in the top and bottom, both of them, the opposite charges, they have attractive mechanism. And the repulsive mechanism is between the same type of charges, and that mainly happens between the positive charges on the ground layer and the positive charges on the top layer. So that's why, and this JB is the main contribution of attractive mechanism, because it, you see the arrow shows that it is from positive charge to negative charge, and the JT, it is the result of repulsive mechanism. And here it shows, you see the direction, because of the positive charges on the ground layer, it repulses the positive charges on the top layer. So that's why the positive charges curves toward the top of the patch, from the bottom to top of the patch. So this is what the diagram shows. Okay, the flow of positive charge. So now what it says that when the width of patch or substrate is very small, and when the height of substrate is very small, so this will be very negligible. JT will be negligible. So mainly what will remain is the JB. So J subscript B is the charge flow between say different type of charges, and happens between because of attractive mechanism. So that is why this JB is important. Okay, so that you remember, this the main contribution of the charge flow is behind the patch between defined opposite charge layers. So now we saw how it was happening. Because of these charges, there are charges mainly in the bottom of the patch. Okay, but this size charges or JT, so this side charges is negligible. So can you visualize this rectangular or this cube like shape in the right side? That is what is showing the it is showing the actual cavity top layer top is the patch layer and the bottom is the ground layer. In between we have the substrate. Okay, so now it says there is almost zero charge flow in the side walls. So that's why this JT is 0, and because this side wall charge flow is 0, so that's why there will be 0 tangential magnetic field. Okay, so now why it will be like this? The tangential magnetic field from Maxwell's boundary condition, what we get is that neta cross H, what the tangential component of magnetic field equals the linear current density, right? So now because this current density on the side layers are 0, that's why the tangential magnetic field would be 0. And that's why this is called a perfect magnetic boundary. In normal perfect electrical boundary, what happens is that there will be charge flow in the boundaries, okay? And generally the tangential electric field is 0 on normal PEC or perfect electrical conductor. But in perfect magnetic conductor, it is opposite. Tangential component of magnetic field is 0, but tangential component of electric field may be non-zero. Okay. So this table I showed the other day. So is it clear the difference between PEC and PMC and how it originates here? Yeah.
Yes, sir.
Yes, sir.
Okay. Okay. So let's go to the next way. So now we'll start the discussion of fringe field. Okay. So fringe field is why important, because the fringe field only it actually causes the radiation from patch antenna. If there are no fringe field, it will be equivalent to a microstrip circuit, because then the electric field will be tightly bound between two metallic plates, top patch and bottom ground. Okay, if there are no fringe outside, they will be tightly coupled between these metallic layers and there will be no radiation. And that's why the fringing is very vital for microstrip antenna. So now see what this picture says. So, patch antenna is ideally viewed as an open circuit transmission line. So, how is it open? You can see that both left and right side is open, right? So, that is how we can consider it as a transmission line where both ends are open circuit. And now, in open circuit, what happens? Open circuit, the current would be 0. At the open end, obviously, current is 0 and voltage will be maximum, right? So, that is what you see here. um, So that's why you see that the electric field also, you see this is in the left side picture. It shows the electric field configuration. At the right side it is maximum, and as well as left side. In between it becomes 0. If you remember, the length of L is lambda by 2. Okay. So in lambda by 2, what happens? The field goes through one half wavelength variation. Okay. So half wavelength variation means it will go from positive maxima peak to negative peak. So that is what is happening. You see in the left side, the arrow shows upward, and the right side, the arrow shows uh, towards the bottom. Okay. And in between it becomes 0. So that means it is one half cycle variation, because L is almost equals to lambda by 2. So now what happens? This is like, now because of fringing field, there would not be like exactly like that. In the picture in the middle with fringing, you see there are some fields coming out of the right side and left side as well, and it is curved or cylindrical, like fields coming towards bottom. Not only perpendicular, but there are some horizontal component also. So this blue arrow, if you see in the middle picture, this blue arrow is the horizontal component, and because this horizontal component is the actual component responsible for our radiation. So that you remember, the top and bottom side, the electric field components in the other two sides, they are vertical, but in the other two layers, the blue arrows in both sides are same direction. Okay, so that is why they contribute to radiation. Electric fields are opposite, but the vertical component of electric fields, they are in opposite direction, but the blue arrow, it shows they are in same direction. the horizontal component. So that is why they will lead to radiation. So now what happens, what is saying that, fringing electric fields on leading and trailing edges of the microstrip antenna adds up in phase. Okay. So in both antenna, they have same direction, these blue arrows. So that's why when they radiate, they adds up in phase and they produce radiation for the microstrip antenna. But the current also, if you see, this is the voltage. Okay, electric field means voltage. If you see the current diagram, they also add some in phase, but the current, equal current will be also there on the ground plane. So that cancels the radiation. And it is equivalent to almost like microstrip transmission line also. It shows why microstrip transmission line will not radiate, but microstrip patch antenna does. So what happens that the current will be there on the top patch layer as well as on bottom ground layer, but they are in opposite direction, so they will cancel the radiation. Okay, so that's why microstrip transmission line does not radiate. But here what happens that we excite the field, or we design the patch antenna such that this fringing will happen, and ultimately this voltage configuration at two sides will adds up in phase and they ultimately radiate. So that's why this happens because of the voltage configuration, not current configuration. So that's why the microstrip patch antenna is called voltage radiator, but not where in other dipole antenna or loop antenna. All this, if you see, their basic analysis is done through current analysis. Okay, so they are called current radiator, but here the main radiation comes from the voltage components. Okay, that is why patch antenna is a voltage radiator. Yeah, so is there any question on this? Is it clear? Okay, okay. Okay, so let's go to the next slide. So if you look more into the fringing field, so you see what happens. Uh, there are two main contributions or two main characteristics of patch antenna which affects this fringing field. What are those? So one is the height of substrate, another is the permittivity of substrate. So those are very vital. So there is a boundary or difference between microstrip line and microstrip antenna. So who will radiate and who will like act like a circuit, that depends on this selection or design of H and ER. I mean height of substrate and permittivity of substrate. See which is what. So it says the smaller the dielectric constant epsilon r of the substrate, the fringing field is greater. So as you generally we take from from 2 to 12, in this broad range we can select the dielectricity from range from starting from around 2 to epsilon r of 12. Okay, in this broad range we can select. So it says as you go towards the smaller dielectricity, smaller epsilon r, the fringing field is greater, and because field bows away further from the patch. So this bow away means as it bows more and more, that means the horizontal component will be more, right? So when epsilon r is small, then this happens, and the smaller permittivity of microstrip yields more efficient radiation. And in reversely, if you take a larger dielectric constant, the electric field fringing will be more confined to between this. The fringing will be less. So that's why then a larger dielectricity is better for microstrip line. Okay, and the when no radiation is
So,
desired, the
so larger dielectric or smaller one?
larger
No.
dielectricity is needed for microstrip line or microstrip
Okay.
circuit.
Okay.
Okay, yeah, and when there is no radiation, a high value of epsilon r is required. That is what he's saying. When no radiation required means it should be transmission line. Okay, So high epsilon r causes the field to become more tightly bound. And another component, what I forgot to write here, is the height or height of substrate. As you reduce the height of substrate, what happens? Obviously, the space between the ground and patch becomes less. So they will be more tightly bound. The electric field will be more tightly bound. So that will be better for microstube line. But as you increase the substrate height, there will be more and more, fringing happening. That's why, higher substrate height, or like greater the substrate height, better the fringing and better radiation. Yeah, so there, like for microstream antenna, two conditions are favorable. One is smaller dielectricity, and second is a larger substrate height. These are two conditions. Okay. So yeah, is it understood?
Yes, sir.
Okay.
So that is why, because that air gap is also included in between ground and substrate, means in order to increase the total height. Uh,
Uh, no, not
no.
really.
Okay.
See, if you just want to do, more physical analysis, if you want to see analytically, you know, um, from Maxwell equation, we know that that delta dot the divergence of electric flux depends on rho by epsilon naught, right? If you
Gauss's law.
remember, right? Rho by
Oh,
epsilon naught.
mm,
So now what happens? So this divergence is inversely proportional to permittivity.
permittivity. Okay.
Remember, right? So
Yeah.
that means if you reduce the permittivity, so what happens? The divergence increases in that point, right? So in the right side or left side, at the boundary between these two layers, so there will be more divergence of field at that point, any point. Okay. So that's why the field will be more divergent in the boundary between the substrate and air. Okay. So that is how it comes from Maxwell equation only.
Okay.
Yeah. Now we will look into the most important components. Those are the what are the modes. Okay. So before that, I want to know that you remember basic about the modes. Do you remember the TEM modes of parallel plate waveguide or rectangular waveguide? Anything? Yeah. T mode, TM mode.
Yes, sir.
Okay, okay. Because those will be required. If you just for recapitulation, I'll let you know like what are the basic things. So TE or TM is like transverse electric or transverse magnetic field, and the more basic is TM, transverse electromagnetic field. Okay. So what happens is like when wave propagates, in the direction of propagation, is there any electric field or magnetic field? That is what we want to see. If in the direction of propagation there is no component, that means if that component is called longitudinal component, and the perpendicular component are called transverse component. Perpendicular to what? Perpendicular to propagation, direction of propagation. Okay. So now if there is no component in the no longitudinal component of electric field or magnetic field, it is called TEM mode. That is, both of them are transverse component, right? And in some cases, in the TE case, what happens? Transverse electric magnetic field may have longitudinal component, but electric field does not. That is why it is called TE. And so, and TM mode is like the reverse. Generally, these modes you can see in the waveguide you can have this all these modes. So maybe if you don't remember, you go through these ones and will have a better memory. So let us see now here how this TEM mode, only TM mode is here. We'll see how TM mode is excited in microstrip antenna. So yeah, what it says, The picture shows, as usual, the cavity where the top layer is the patch and bottom layer is the ground plane, and in between is the substrate. It shows the thickness of the microstrip is usually very small. Yeah, that is right. Obviously, the substrate height is very small, and wave generated within the dielectric substrate between the patch and the ground plane undergo considerable reflection. Okay. So obviously, when the wave is generated between the plates, in the metal, the wave does not propagate. It happens in the dielectric only. In between these two dielectric metals, there is the substrate. There, the wave go through multiple reflection between the two metallic layers. It's as if like a, waveguide, right? And fields beneath the patch. That's why both of them generate a standing wave. When they have multiple reflections, you remember, they form standing wave, and that can be represented as sinusoidal wave function. When the height of substrate is very small, that means h is way smaller compared to lambda, then field variation along the height will be considered constant. So across the height there is almost zero variation because it is very small. So the variation happens in which direction? You see, there are x, y, and z coordinates. You see, so along x component, x direction is the height. There is negligible variance. So along y direction is the direction of propagation. Why? Because the field will go multiple reflections and ultimately it will propagate through plus y or minus y direction, right? Because of standing wave. So we will have substantial variation across y direction. And also, because the substrate height is small, fringing of the fields along the edges of patch are also very small. Why the electric field is nearly normal to the surface of the patch. Okay. Yeah, that is obviously, it is there is the fringing is almost negligible along the edges. Okay, so that is why we consider them almost perpendicular to the surface. So now what happens, only TMX, transverse magnetic, X is, if we consider the propagation or like with respect to X direction, it is transverse magnetic, means there are no magnetic field component in direction of x. That is why it is transverse magnetic with respect to x direction. Yeah, is this understandable? Do you understand this nomenclature TMX? It is different to normal mode nomenclature, right? There we call TE or TM with respect to direction of propagation. But here you see we have all the fields are confined between this cavity, right? There is no such propagation or something. So that's why it is actually described in terms of some x, y, or z direction. So TMX means TM mode with respect to x direction. Yeah, so yeah, is it clear this TMX nomenclature?
So I think some network issue. Voice is breaking. Hello.
Hello, can you hear me now?
Yeah. So
Yes, sir.
Okay.
okay.
So, okay. So, from which portion did you not hear?
I think that is so from TMX field.
Yeah. So
Uh,
there only I was. So, do you understand this nomenclature of TMX mode? How it is described? I said that TMX means it is defined. This nomenclature is defined from normal TE or TM mode, right? Because there you have a propagation of wave. Here we don't have any propagation as such because it is the fields are confined between the cavity walls. Okay. So here it is defined in terms of some direction, x, y, or z. So here x direction, TM mode with respect to x direction means there are no electric field in the direction of x. On the only the transverse to x plane, there will be electric field.
Yes,
Yeah. So is it okay? Okay. Okay. So now you see what is saying. So now coming from our last uh, from last PPT, where we showed that the four walls, they behave like perfect magnetic conductor, right? Because there are no negligible current flow between these side walls, so it behaves like perfect magnetic conductor. So now see, if there are no tangential components in this direction, so that means neither x component nor y component. I mean, sorry, neither, yeah, right. So this side walls, you see, this side walls it is in the direction of, in the y and x, right? X, y, in the xy plane, as well as xz plane. So some of the side walls, they are in xz plane, xy plane, as well as yz plane. Okay, if there are no tangential components, that means there will be no x component also, neither. Okay, so that is how it becomes like a TMX mode. There will be no magnetic field component in the x direction. Yeah, is it clear? Because they see in all of these walls, the x component is common. X component is one of the tangential components in all of these. So the x component is not present in none of the side walls. Is it clear? No, because see last slide, what did you see here? Here we saw that there are no current on these four side walls, no surface current, and because of that no surface current, there are no tangential magnetic field. So tangential magnetic field will be in all the direct, on all of them will be in the x direction. You see, in all of these walls, the tangential field will be in x direction. So that would be zero in all the side walls. Yeah. Do you have any question? Yeah. So because of that, it is TMX mode, transverse magnetic X mode. In the X direction, there is no component of magnetic field. Right? Now, okay. So let's go forward.
Sir, what can it be if it is TA?
Sorry.
So how that configuration will it be for TA? Sorry,
T
TMY.
TMY. So if it is TMY, that means there should not be any magnetic field component in the Y direction. There should not be any magnetic field in the Y direction. That should be the thing. TMY. And similarly, if you have TX means there should not be any electric field component in the X direction. Okay.
Okay.
Okay. Now see what are the equations. So if you if you visit the Balanis book, so there is like a lot of equations and analysis. So because all the field configurations and all, you can mathematically calculate all this. There is nothing like you need to do simulation or anything. Those are all analytical equations. So I will just note down the basic equations, and if you want further in-depth analysis, you can follow the Balanis book itself. So see, generally what we solve is the wave equation, right? In any of our field configuration or area, like waveguide or parallel plate waveguide, even in our basic two-wire transmission line, we always solve our uh, wave equation. Usually this wave equation is called Helmholtz equation, right? So this AX is called vector potential AX. If you remember from electromagnetics, we generally solve this kind of equation. So grad square AX plus k square AX equals 0. That is the wave equation for propagation, where k is the wave number, 2 pi by lambda, right? And if you see that, if you solve this equation, generally the solution will be in terms of there will be cos kx, cos ky, and cos kz, all these forms. So now the question, this is like you can have a basic intuition why this is cos kx cos ky variation. So basically, you see the again in this all this length variation x y z will have a cosine or cos or sine variation because of the standing wave formation. If you remember, there are multiple reflection between these walls. That's why we have a standing wave variation. Now what happens, because the top and bottom layer are metallic, so there has to be maximum uh, current will be maximum there and voltage would be zero, right? So that's why it would be cos variation. If you remember in cos, what happens in between it becomes zero, half wavelength variation. In between, in the center it is zero, and the both ends it is maximum. It is reversed to sine, right? So cos what happens at the beginning at phase zero it becomes maximum, and in the middle it has phase opposite phase. So it happens mainly because at the end or at the at two ends of metallic cavity we have zero voltage and maximum current. That is why this vector potential will also be this kind of variation, cos variation. And this kx ky generally gives you the the relation with wavelength. So how many wavelength will be there, so that is what it talks about. How many, if you remember, in the rectangular waveguide we used to say how many half wavelength variation we have. A L cross, if you have a cross b, aperture of rectangular waveguide, so we used to say T10. T10 means, so 1 means in x direction there is one half wave variation, half wavelength variation, and 0 means there is no half wavelength variation in the other dimension. Okay. So here also accordingly x, y, z in all the directions, how many half wavelength variation, that will be defined by kx, ky, kz. So where kx is like 2 pi by lambda x, ky is 2 pi by lambda y, like that. And the third equation, it says this is the dispersion equation. So you see, so this equation you must have seen for all the waveguides, right? Even rectangular waveguide, this is very famous. From here you generally calculate the cutoff frequency of any waveguide. So this is also called dispersion equation. So this kx, ky, kz, these are the length. Sorry, these are the values of m pi by h, n pi by l. See, h, l, and w. These are the length in these three components, x, y, and z dimension, and that is equals to kr. So this is the composite wave number, and that is equal to omega square mu epsilon. Omega square is the frequency, cutoff frequency. Mu epsilon is the properties of this substrate. So from that, why it is important? From this FR is the cutoff frequency or the frequency of the resonance frequency of any particular mode. So based on this M and P are the integer numbers from 0 to 1 to anything. Okay. So based on those values, you can now calculate the frequency. So FR, M and P is calculated from that third equation. You get this kind of variation. This is the equation for any resonant cavity. Even similar equation is there for waveguide. So obviously, if you M, N, and P, this is how many half wavelength variation in X, Y, and Z direction. If you know that, that will give you the resonant frequency of your patch antenna. That will be your approximate resonant frequency, right? So that is why this mode configuration is very vital. So you can calculate your resonant frequency from these numbers. So yeah, do you understand this? How the this resonant frequency is derived and all, how it is?
Yes, sir.
Okay, okay. But yeah, you see this, the now for TEM mode, we have to see this M, N, and P. You remember in M and P, in which direction they are defined. Okay, you see, M is defined in H, L, and W. M is defined in the H means X direction, right? And N is related to L. L is in which direction? It is Y. and P is in W direction, that means W is in the Z direction. Okay, so that you notice in X, Y, and Z direction, M, N, and P are defined. So now in the next slide, we'll see how these field configurations will look like. If we have defined value of M, N, and P, let's say 0, 1, 0, 1, 0, 1, that is how we calculate, right? TE 101, TM 010, like that. So these subscripts will be saying, so what are these values of M, N, and P? Okay, so that is why these equations are very vital. So you need to only remember the last equation, FR, value of FR. Yeah, now you see how this field configuration looks like. So we will start from the left one. Okay, so we'll go from left to right. So let's see these are what would be the dominant mode. In every field waveguide or anything, we have a configuration or we have a concept of dominant mode. So that means which is the lowest order mode. Okay, lowest order mode means which has the lowest cutoff frequency. That is called dominant mode. So because if you just excite, that would be the first mode, and it will have maximum power in that mode only, right? So what is that mode? That mode is FR010. That means this is TM mode. You see TMX mode 010. So what happens? The X component will always generally people X component we don't calculate because X is not important. There is no variation in X, right? TMX. So you will say TM10 or TM01, TM20. So three of the subscripts are generally not required, but you can just still remember. But X component we neglect. So so now you see how this field configuration looks like in the leftmost picture. So 010 means you see the X component, X direction, all the fields are same. All of them are vertical, right? So there is no variation in X direction. If you go along the X, if you see along the X direction, there is no variation. Okay. And now if you see in the Y direction, there is one half wavelength variation. Across the length, if you remember, across the length is our Y direction. So there you see there is one half wavelength variation. That is called 1. So here our M is 0, N is 1, and P is again 0. So yeah, so this half wavelength variation, we have already seen this. This is the basic mode of any micro patch antenna, right? So that happens because of we saw it is behaved like a open circuit transmission line. So both ends, left and right ends, have opposite field configurations. So this is again a cos theta variation. You see, both ends are positive and negative, and in between is goes 0 in a half wavelength lambda by 2. So and the frequency you can calculate from the previous equation. From here, previous equation we had this. Here if you put Mn and P values, you will get this 1 by 2L square root of mu epsilon. So you can calculate like this. So is the first mode clear? TM010 mode. So this is the most important in every, if you read any paper or anything, they will mostly give this configuration.
Yes, sir. It is okay.
Okay. But do you see this dominant mode? Here I
Mm.
have given a condition. Is L greater than W greater than H. Do you understand this? Why this configuration? You tell me now.
Because variation is along the lengthwise only.
Lengthwise
Uh,
only. Uh-huh.
Means
Okay, but why
uh,
L has to be greater than W? Yeah, Binay. Yeah, so Binay, can you tell why L has to be greater than W for dominant mode here?
So for resonance, frequency resonance.
No, no. So I told you tell me now what is dominant mode? How do you define
Mode,
what which you yeah
Ha,
mode
which
with
has
the
lowest
lowest
cutoff.
cutoff frequency.
lowest frequency, right?
Mm.
Now what you see in the last slide, what was the definition of frequency? It was m pi n m n and p, right? And
Mm.
in the denominator what we have, L and W is in the
The
denominator.
dimensions. Okay.
So now from here can you understand why it has to be L greater than W for this mode to be dominant? Do you
If
understand?
L is greater means denominator is greater means that term will be smaller, no?
Smaller, right? Exactly,
Become
exactly.
smaller.
So if it is
It's
reverse, if
yeah.
W is greater than L, then what would happen? This P 01 mode would be the dominant mode, not 010. 001 mode
Yes.
will be dominant. Do you understand? You see, exactly that is the same.
So
Yeah, in
can
the
you
second,
repeat? My
yeah,
network issue. So can you
ah,
repeat?
okay, okay,
Yes, sir.
yeah. Can you yeah, Binay, could you hear?
Yes, sir. I can. I can.
You can hear. So Nandana, yeah, I think it is in your end only. Okay, can you hear me, Nandana?
Now it's okay, sir.
Okay,
Hello.
okay. Yeah. So now, yeah, I
Okay.
will repeat
Um,
once. You see here.
okay. Okay.
So what happens is that if L is greater than W, so that means 010 mode will be dominant. And if W is greater than L,
Okay.
so what happens? 001. 001 mode will be dominant because that frequency will be less than 00010 mode. Right?
Okay. Yeah.
So that is what is shown in the second picture. In the second picture is you see TM001 mode. So here P is non 1 and others are 0. So here in the bottom you see it would be generally it would be second order mode for L greater than W. But if it is opposite, if W greater than L, then it would be dominant mode in that case. Yeah. Is this clear? Is the definition clear?
Yes.
Okay. So and
Okay,
you
sir.
see, yeah, you see the equation also. The value of effort 001, it is the same, exactly same. If you put on the M and P values here, it would come to this. And what you have to notice is main thing is the field configuration. Here you see the field variation how it is defined from the first one. Now we have field variation along the W side. That means along our Z direction. So along Z direction, we have half wavelength variation. But now across L, there is no variation. So that is called 001 mode. So similarly, you can get TM020 mode. So in 020 mode, you see across our Y direction, we have two half cycle variation. Two half cycle means one full wavelength variation. One full cycle variation. So that is what it shows. If you see, that means this is the variation what you see in there. Across L, we have two half cycle variation. It starts from positive peak towards upward peak, and again in the right side, it comes back to right upward arrow. Okay. In our first 010 mode, if you notice in the left side, we have upward arrow. In the right side, we have bottomward arrow. But here it is both same. Both side we have upward arrow. That means it is a full cycle variation. Means two half wavelength variation, two half cycle variation. I should not say half wavelength because length is always half wavelength, but half cycle variation. Why half cycle? Because it is standing wavelength variation. Standing wavelength, if you remember, the whole half, full cycle variation happens in lambda by 2, not in lambda. Okay, so that is the difference between standing wave and normal wave. So yeah, you must remember that. I guess you remember from every transmission line variation also. So transmission line also you will see in lambda by 2 only you will have 360-degree or full cycle variation. And in lambda by 4 you will have half cycle variation. So that is what you see. In L equals lambda by 2 here always. But sometimes it is half cycle variation, sometimes full cycle variation. Okay, so based on these two also here you can calculate the modes, and similarly you can see the TM002 mode also how it looks. So yeah, is this clear? This is very vital if you want to actually understand what is happening in patch antenna. This is the backbone of all analysis in patch antenna. So is this clear to you? No, you ask me any question you have. If you understand this, so almost most of the things it will be clear from here. And the beautiful thing is if you do any patch antenna simulation in CST, you can actually see the field variation like this, exactly like this you will find in CST simulation or HFSS simulation, however.
Okay, sir. So now we have 1 0 1 0 0 means two. How many? Is there any limit in this? That is the
No, there is
number
no. You
up
see,
to.
these are called
Oh,
second order, third order, fourth order modes, right? So, uh,
okay.
so now the thing is like which order mode is important for you? Yeah. So how do you excite it? Yeah, you now tell me
Okay.
how it will be excited. Any waveguide or any antenna, you say, how do you excite this? This is the configuration. If you provide energy in this configuration, this field will be like this. But how do you provide the energy in
Okay.
this configuration? Yeah, that is the question. So generally what happens, we generally provide, some kind of excitation. And based on that, our energy, or like say, we generally use coaxial cable to excite our antenna, right? Okay. Mm. So you excite this antenna at which frequency, which resonant frequency, based on that, these modes will be excited. Is it understood? So this generally, these modes can exist all of them. Okay. So now it will depend in your antenna, what antenna you fabricate or simulate, which mode exactly which mode will be excited or which mode will be in work. That depends on you provide your energy or excitation at which frequency. Let's say you give in a band of frequency, like let's say this 010 mode in 2 is 2 gigahertz, 001 mode is 2.5 gigahertz, and 020 mode is 3 gigahertz, right? Now if you provide a simulation, your frequency band of simulation is 2.5 to um, uh, 3 gigahertz, so both 010 and 001 mode will be excited. But which mode will have maximum power is the lowest order mode. That you must remember. Always the lowest order, lower order modes will have more power from your excitation. So they will have a upper hand over the higher order modes. So they will be more prominent. So this is for our antenna. But generally in a
Okay.
waveguide, what happens? Uh, yeah, in a waveguide, what happens if you need any particular like T10 mode or T01 mode, you have to excite in that particular configuration. So you must go through once through that to remember that you have a defined kind of pins or coaxial, the conductor pins, bent pins or like that we use to excite these modes. So you need particular kind of excitation there also to excite a particular mode. But here it will depend more on the energy or like in the frequency band of your excitation, it will depend. Yeah, now tell me, is it what are the questions you have? So yeah, you must have questions here because like it took me long time to understand all these things. So yeah, you maybe now only you want to understand, but later on also you tell me. There must be questions on this. And the main thing is like just by seeing this you will not understand. You take a very basic patch antenna and simulate at different frequencies, and you can see the field configuration. Then only it will be clear. Is it valid? How is it happening? Yeah, now you ask me, Binay.
Sir, if I design, I mean, once I design an antenna, so that more resonance will happen on dominant mode, or like it can happen anywhere, like more S11.
No, more
Like,
dominant mode is fixed, but you can choose to excite other modes also. That will not be the problem is that will not be good. Will not be power efficient that much. If you see, so that is what I am saying. So antenna, one of the main characteristics is radiation efficiency, right? So if you excite the
yes,
antenna only at dominant mode, so very less energy will be wasted in the the losses in the waveguide, losses in the cavity modes. So antenna efficiency will be more. Now, if you choose to excite the same antenna in the third order mode or fourth order mode, there will be more and more losses in the cavity because of metallic loss, dielectric loss. So that's why antenna radiation efficiency reduces.
sir. My doubt is like, if I design an antenna, so it
Mm-hmm.
it is resonating at multiple frequencies. So first it will resonate at 2 GHz, and later on
Mm-hmm.
3, sorry, 4, and later
Mm-hmm.
on 7.
Mm-hmm.
So how to take that? Which one is dominant mode frequency?
So yeah, see, whichever you will design the antenna for some band, right?
Yes,
You will
sir.
have
For
maybe
using
some
formula.
yeah
Yes,
you will have some frequency in your consideration, right?
yes,
Let's say you want to design antenna at 2.5 gigahertz, right?
yes,
So that obviously you want in the dominant mode because it will be the most efficient antenna. Is it understood or not, right?
yes.
Yeah, so this is dominant mode, then you will obviously go for FR010. That is what we do. So we calculate the value of L and W such that your resonant frequency for TM10 mode will be your dominant mode, your required 2.5 gigahertz. So now, yeah, I think you might have forgotten. Let me remember you. Few classes back, I showed you how to design the antenna. Here, if you see what we had done, we started
Yes,
from
sir.
E epsilon, frequency, and H. Those are specified, right? Substrate height, substrate permittivity, and frequency. Frequency is already you have to know first which frequency you have to design. So now we determine W and L. W is this, and L is lambda by 2 always. So W we have to calculate from this. These are all calculated in because lambda L equals lambda by 2. See this frequency FR010 is, you see, we all take TM010 mode because that is our dominant mode. So all this antenna design and everything is done with respect to 010 mode. Yeah. So now is it clear?
10.
Yeah.
Yes, sir.
Okay. No. Yeah. You think more about it, but until unless you do a simulation and see this field configuration yourself, you will not understand properly. You have to do. It is very easy. It will. A patch antenna design now you can do in 5 minutes or so. It is available YouTube. So many
Yes.
tutorials are available. You just do it once and simulate with excited with different frequency bands and see if these things are varying or not. The field configuration you have to notice. Okay. Yeah. Nandana, do you have any question?
Um, no, sir. It is
Yeah.
clear
Yeah.
now. Yeah.
Okay. Okay. So maybe okay. I will take a 5-10 minutes break and we'll come back. Okay. So you will also take a break. We'll meet at 45, 6:45. Okay.
Okay.
Okay. Are you here, Nandan and Binay?
Yes, sir.
Yes.
Okay. Okay. So we'll start from this. Okay. So now I'll we'll look into two very vital theorems in electromagnetics. So one is uniqueness theorem, another is surface equivalence principle. Okay. Um, did any one of you read about this before? Uniqueness theorem and surface equivalence principle. Did you hear about it?
I couldn't recall it.
No, sir.
Okay. Okay. So see, these are the kind of backbones of much of the electromagnetics. Okay. So many where you will see this. So yeah, we must have a overview of this too for the rest of our analysis. Okay. So these are very important. So look it very carefully. Okay, and ask me any question if you have. So if you don't understand this, then rest of the part you cannot understand properly. Okay, like while learning this antenna and all, I myself had a lot of questions. So I had to learn all these things and read properly. So I want you also to understand this. So what is uniqueness theorem? So there is, all the equations, all our problems in electromagnetics, we generally solve Maxwell equations, right? So from Maxwell equation, we get the Helmholtz or Laplace wave equation. Then we solve the value of either electric field, magnetic field, or the magnetic vector potential, all of this from these equations. Now the thing is that any of the equation can have multiple solutions. Like let's say in our wave equation only in terms of electric field, there can be multiple solutions. So how do we know that this solution is the only solution? If there are many solutions, then we'll be confused, right? We don't know which one to take. So we want a unique solution. So that is what is given by uniqueness theorem. So in our electromagnetics problems, what are the conditions so that we will have a unique solution? That is all about uniqueness theorem. So yeah, so that is what it says. Like when a problem is solved, there can be multiple solutions, but we want a unique solution so that we are assured that this will be always the case. Okay. So most of the cases we have our equations, electric field curl equation and magnetic field curl equation uh, from our Maxwell equation like this in terms of curl of E is the if you remember uh, these are the equations. I hope you remember this. So I hope you have seen JC is the current density of conducting and incident in current density. And EMI is the term you might not have seen. This is magnetic source, magnetic current density. So magnetic current density is a term which does not exist in reality. But for the sake of simplicity, we assume it. Like as if we have the imaginary numbers like a plus b format. We know that imaginary numbers are not real, but still for the sake of our analysis we use it. So this magnetic current density EMI is a similar term which does not exist, but for sake of our solution or sake of simplicity we assume it. Okay. So our uh, modified Carl equation of Maxwell, it becomes in terms of, if you incorporate all these terms, it becomes like this format. So now what uniqueness theorem says is that a field in a lossy region, now you see it has to be a lossy region, there has to be some loss in some region created by these sources, current density and magnetic density, is unique. So for this, current sources, why these sources are required? Because in all the our antenna analysis and all, our basic analysis is done through current source or magnetic source. Okay, we use this for excitation. So that is why they are saying if we have these sources, then the solution means in terms of electric field and magnetic field, is unique within that region when this one of the three condition is satisfied. So let's see the satisfied. When the tangential component of electric field over the boundary is specified. So we have a region. Region means it's a volume, right? So over the surface of this volume, we need to have the electric field, tangential electric field component specified everywhere. So that is determined by, that is also mentioned by neta cross E. Neta is the, neta is the surface perpendicular to the surface, normal to surface, okay, and E is the electric field. So if you take normal neta cross E, that will give you the tangential component. Second condition says you should have tangential component H is mentioned over this boundary, or the third you said like any one of these has to be satisfied, any one of these three. The third one says the former, I mean, either electric field of tangential components over some portion of the boundary, and the rest of the boundary, the tangential component of magnetic field has to be specified. Okay, so either you need tangential component of electric field over whole surface or whole boundary surface, or the tangential component of magnetic field over whole surface. Otherwise, you need some portion of the surface electric tangential component and some portion rest of the boundary tangential component of magnetic field. If you know any one of these three, then you can uniquely get the electric field or magnetic field solution in this lossy region. So yeah, now you tell me what is not understood from here. Is it first you have to see, you have to ask question like, why are you studying this? What is the role of this? Then we understand like this. Okay, so that is what I first said. What is the problem? Why we need this at all? And then what are the conditions for to get this? Is it clear? Is the problem clear first and then the statement or solution?
It is not clear, sir. I didn't understand.
Yeah. So
This is
which
the
portion
first
is?
time actually I'm.
That's okay. That
That's
is
why.
okay. So that is why I'm saying, is the problem clear? Why do we need uniqueness theorem?
To get a obtain the solution.
Obtain the solution. That's why.
So,
So, yeah, I told you, no.
uh,
If you solve our equations, this curl equals C, curl equals H. If you solve, so generally what do you get? This equation of partial derivatives. If you remember del square E, del square H. This solution, you see the first one, grad square A, grad k square X. So grad square is if you have a term of dou x square, dou 2 dou y2 like this. So these are partial derivative equations, right? If you remember from basic electromagnetics, there are a lot of partial derivative equations, right? Right or not?
yes, sir.
So, yeah. So there were d2y dx2 like that, second order equations in electromagnetics. So now if you solve these equations, there can be many solutions, right? There are many solutions possible. So what are the conditions? What are the conditions you should know to get a unique solution? That is what we want. So that all this comes from the solution of equations. How to solve such that we have a unique solution.
So to
here,
get to get a unique solution, these three, either of these three conditions should be satisfied.
Exactly. Now in electromagnetics, we need to have a unique solution in terms of electric field or magnetic field, right? Yeah. So then how will you get? They say inside a lossy region, if we need to know the boundary conditions. In the boundary conditions of this region, either we should know the electric field or magnetic field, or one of these.
Okay.
Yeah, Binay, is it clear?
Yes, sir.
Okay, so now we will have more of this in pictorial. You will understand better. So the more advanced or more important theorem is surface equivalence theorem. Okay, or it is also called Huygens principle. So we'll see how this theorem needs uniqueness theorem. That is why. So here you see these pictures. Do you see in the bottom right side? So here this this dotted lines is our boundary. Okay, so this this encloses a volume. We need the boundary of this volume, that is S, to understand the we need the boundary conditions on this enclosing volume or enclosing surface S. Okay, so what all these boundary conditions we talked about is on the surface S that encloses this volume. So is it clear from the previous slide what we are talking about? So we are all talking about a volume enclosed like this by a surface S. Okay. On this surface, we need to know the boundary conditions like tangential electric field or tangential magnetic field, or a mixture of this.
Okay.
So now see from that how surface equivalence theorem is important. Let us see. So from the name only you see equivalence. Okay, equivalence means, so many of the times our actual sources is what, this current source or magnetic source, J and M, current density or magnetic density. Okay, but what happens in our solutions? Okay, if we need to find solutions for, let's say, antenna and all, if you have to calculate using these sources all the time, that many of times it becomes very computationally inefficient. It takes a lot of time if you have to solve everything from the basic principle. Okay, if you solve this partial derivative equation from G and M all the time, so it will take a lot of time. So how to reduce this? That is where these are very relevant. This is where the equivalent, we need some kind of equivalence of our problem to reduce the computation, or to solve these problems easily. We need an equivalent problem. That is why this is important, this is required, surface equivalence. So let's say let us assume a problem. Okay, let's say we have an antenna here, and at a 1 kilometer distance we have to calculate field. Okay, so often this is required. Okay, let's not take at 1 kilometer. Let's take at 1 meter. So even at 1 meter distance, you have to calculate this. The equation, through equation you have to calculate this electric field and magnetic field. That means you have to solve Maxwell equation, right? So this Maxwell equation we generally solve using FDTD or method of moments. These computational tools are there, right? So now this whole calculation domain of 1 meter, if you have to calculate, it will take lots of time, right? So some way we need to simplify the problem so that we reduce our computation time, but the solution itself remains same. Solution does not change for both the cases. So that is why we need a equivalent problem. So simplify our solution. So yeah, let's you first tell me, is this question clear? This is the problem. That is why we need a surface equivalence theorem. Now I will state what it is.
Okay, sir. To make it simplified, this equivalence theorem is used. Is that?
Yeah, exactly.
Okay.
Yeah. Yeah. Binay?
Yes, sir.
Okay. So in this picture, so yeah, let's see. So what are actual sources? Or in a case of antenna and transmitter, so actual sources are this current density. In the picture you see, this dotted line encloses J and M. Okay, so J and M, they are expressed by single arrow and double arrow. Okay, so these are replaced by equivalent sources. So these equivalent sources may not be the real solution. Okay, real source. It can be imaginary or fictitious sources. But this gives a equivalent solution within a region because they produce within that region the same fields as the actual sources. Okay, so that is what I'm saying. See, all these things are mathematical things. it does not exist in physically. That is what first thing you have to understand. All this comes into effect to make our problem or problems easier. Okay, mathematically, none of these are physically valid. We create imaginary source or imaginary solution such that ultimately our calculation or solution becomes easier. So that is what it says. We will replace these actual sources by some imaginary or fictitious sources. But that does not matter as long as we get our calculation or electric field, magnetic field at 1 meter distance same. For both the cases, if we get the same, then it does not matter for us, right? So why it is called now Huygens principle is because Huygens principle it comes from optics and all basic physics. It says that if you have each point on a primary wave front can be considered to be a new source of a secondary spherical wave, and the secondary wave front can be constructed as the envelope of these secondary spherical waves. It means if you have a source, okay, and in front of source if you have some kind of surface, so any point on that surface it can be considered as a secondary waveform or secondary source itself, and you can take that secondary source itself for the rest of your calculation. That is what is Huygens principle. So all this basically comes back to this Huygens principle, okay, is equivalent. So now it says, from uniqueness principle, if we know the tangential electric and magnetic fields completely over our boundary surface, then we can, calculate these fields in the outside this boundary uniquely. That is what we got from uniqueness theorem. Can you correlate now?
Yes.
See, uniqueness theorem says what? In that boundary, yes, we need to have tangential electric and magnetic fields. Then we can calculate outside this boundary. There, if you see in the picture, there are two things mentioned, which is V1 and V2. So V1 is the volume enclosed by S, and V2 is outside. So our region of concern is V2, because we need to know at 1 meter distance what is field that is given by E1 H1 at V2. We don't care about what is happening at V1. V1 will enclose by some surface, and we will calculate some equivalent sources on V1 such that at the outside it is same. The solution at outside U1 H1 should be same. So as long as that happens, we don't care what happens inside V1. V1, although you should remember, V1 is actual our source. It contains our actual antenna or something, any other source. That we replace by some equivalent surface, so that our ultimate calculation E1 and H1 it remains same. So now how do we do that? So it says fields outside the imaginary closed surface are obtained by placing on the closed surface S some imaginary electric and magnetic current densities. So that has to satisfy the boundary condition. The moment we put some sources, these imaginary sources on the boundary, it creates a boundary condition. So that has to be valid, and through these imaginary sources we will create the U1 and H1. That is our goal. These imaginary sources comes from the equivalence principle. So now you tell me so far what is not clear. So this is very serious and it takes some time to understand. You have to read carefully and all. So that is why I'm. Should I go slowly and you tell me? Should I repeat?
Sir, we will actually we study these things and we will again ask doubts.
Okay, okay. So yeah, I will stop it in this slide only, so that you go through either Balani's antenna book also. It is very easily. It is very good way it is explained. You go through this and come back tomorrow. Okay, okay. So
Okay, sir.
okay, yeah. So you must read this. This is very important in many of the electromagnetics. You will find it. It is required so much. So I will complete this slide. Now see, they are saying correct densities are selected so that fields inside the closed surface are 0 and outside is equal to the radiation produced by actual sources. So that is what we care about. The fields outside our thing, that is what E1 and H1. So that is what obtain the fields radiated outside a closed surface by sources enclosed within it. We enclose our main sources and have a equivalent surface or equivalent surface that will create E1 and H1. Now what happens that generally we in our enclosing surface we take it as a PEC or PMC, perfect electrical conductor or magnetic conductor, because if you take that, then our either tangential electric field or tangential magnetic fields vanish. There is the condition of PEC or PMC, right? In PEC, tangential electric field vanish, and PMC, tangential magnetic fields vanish. If we enclose our imaginary surface with this, then our calculation becomes easier. So now you see, our this surface itself is imaginary. What we cover with this surface, PEC or PMC, that is also imaginary. But what actually happens, we need to calculate E1 and H1 outside. That is real. Okay, that happens is real. All other rest of the things is imaginary. And it happens only in calculation, not in reality. So that is why, in bold it is written. So remember that JAS and MS, that is the equivalent imaginary sources on the boundary S. That are imaginary sources, and those are enclosed by a imaginary closed surface. The surface itself is imaginary, as well as the sources on the surface. And that creates an equivalent problem so that the field outside E1 and H1 is same. So that is in equivalence principle. So you try to read about this and come up with all the questions you have. So until unless you read this carefully, you won't understand properly. Okay. And then next week, not next week, tomorrow only I will go through the other things. There are a lot of other stuffs on it, very important things. And then I will see, I'll tell you how it is important for our microstrip antenna.
Okay.
Okay. So this you go through Bhavani's antenna book and it will be there.
Okay.
Yeah. So, but I expect that tomorrow you will have lots of questions. Okay.
Okay, sir.
Both uniqueness and surface area, both you go through it. Okay.
Okay.
So maybe we will end it here and then meet tomorrow. Okay. Bye. Bye.
Okay, sir. Bye.
Thank you.
Thank you.